This is a video to help you with the data analysis for this standing waves experiment. For question 1, please upload a picture of the slinky when it is vibrating with the third harmonic. In question 2, we have to annotate diagrams of the standing waves to indicate the nodes where the amplitude is small and the antinodes where the amplitude or where the vibrations or the displacements are large. So let me indicate a node with a letter N and an antinode with a letter A. With the fundamental, we have nodes at each end with an antinode in the middle. With a second harmonic, we have a node at the beginning, a node in the middle, and a node at the end. And we have antinodes, two antinodes at those locations. With the third harmonic, we have two nodes at the ends and two nodes in the middle, and three antinodes. With the fourth harmonic, we have two nodes at the end, three nodes in the middle, and right at these locations where the letters are, we have four antinodes. You can see that at the antinodes, the string is vibrating such that the displacements of the slinky at that point are large. At the node, the oscillations or the distance moved sideways by the slinky is small. So here we can evaluate the theory that the standing waves are only stable when the boundary conditions are met by the shape of the wave. In the case of a fixed string, at both ends, the boundary condition is that at the ends where it's fixed, there must be a node. And then do our results demonstrate that? So you can comment on that. Just type your answer into that box. Now, if we apply Newton's laws to a slinky or a string under tension that is vibrating, we can predict that the shape that the wave takes will be a form of a sine wave. Sine is a trigonometrical function, and here sine is shown as a function of angle. So one wavelength this shows one wavelength. These 2 points have the same amplitude and will also have the same velocity if this were a traveling wave. When we look at the first harmonic, so let me just go back to over here, we see that this distance L actually represents half a wavelength. You can see we only have the top part, this part here, and the rest of the wavelength would be something like this. I haven't drawn it to scale because I don't have enough space, but we can see that for the first harmonic, this length represents the wavelength given by the symbol lambda divided by 2. So this would be for the fundamental. For the first overtone, this length represents the wavelength of the first overtone. The length of the string in this case is equal to 3/2 wavelengths of the second overtone. And here we can see that the length of the string from there to there is equal to 2 wavelengths of the third overtone. And we can put these results into our table. Now they're asking for lambda as a multiple of L. What we're going to do, we're going to rearrange these equations right here to give us that lambda naught is equal to 2L. So this is equal to 2 times L. This is just equal to L. For the third harmonic, which is the second overtone, we see that L, 2L over 3 is equal to lambda over 2. I'm just rearranging this equation. So that's 2L over 3. And in the last case, we see that the wavelength is going to equal L over 2. So let's put that over here. Now this is the classic equation relating the frequency of a wave, which is given by the value f, or the symbol f, multiplied by lambda, which is the wavelength, will equal the velocity of the wave. When we do the experiment by seeing how a pulse travels down the slinky and reflects from the other end, if we'd measured the time or the distance divided by the time taken, we would have got the velocity of the wave. By rearranging this equation, we can see that the frequency of the wave is going to equal v, the velocity, divided by lambda. So we know our lambda. If we take v and divide by this quantity, we will get the frequencies. So I'm going to copy this because those are the wavelengths. Just going to put them off to the side here so I can refer to them. This is lambda. We see that in order to calculate the frequency, we need to calculate v over lambda. So the frequency here would be v over 2L, because lambda is 2L. For the burst overtone, the frequency is v over L. For the third overtone, the frequency is 3v over 2L. I'm dividing v by this number, and for the last one, the frequency is 2v over L. What does this now tell us? This is equal to the fundamental frequency, and this frequency divided by the fundamental, that's just 1. So I'm dividing all of these by this quantity. We can see that this is equal to twice that. This is 3 times the fundamental, and this is 4 times the fundamental. So this tells us that what I'm trying to get across here is that for a string, a stretched string or a stretched slinky, the harmonics occur in multiples of the fundamental frequency. And this is seen in when, for instance, a guitar string is plucked, it will vibrate at all of the harmonic frequencies to differing extents. And this will combine to give the rich tone that we associate with a stringed instrument. So in the second part, we have to, or in part number 6 here, we have to write our experiment values for the first and second harmonics we obtained for the experiment with the mailing tube when one end was closed. In my experiments, I got 132 Hertz for the first harmonic and 400 Hertz for the second harmonic. Let's calculate the theoretical values and see how close we got to that. What's happening is that the standing waves in a tube that's open at one end will have a flow node where the tube is closed, because the air cannot move there, and we'll have a flow antinode where the tube is open. This is actually a quarter of a wavelength. If I were to sketch a full wavelength, you can see that this here is a quarter of the wavelength. So what this means is that the length of the tube, when it's resonating with its fundamental frequency, represents a quarter wavelength of that note. Therefore, the wavelength is equal to 4 times the length of the tube. Therefore, the fundamental frequency is going to equal V divided by 4L. We know V is the speed of sound, and the approximate value for that is 340 meters per second. Now let's look at the standing wave for the second overtone, the first overtone or the second harmonic. We're going to have a flow node at this end, and we need to have a flow antinode at the open end. This is closed, and this is the open end. So what kind of shape would have a node here and an antinode at this part? Well, we have this, but then the next the next waveform that will have those characteristics is this shape. And we can see that what we have here is that the length of the tube is equal to 3/4 of the wavelength. Therefore, this length represents 3/4 of the wavelength of the sound in the tube when it is resonating with the second harmonic. So therefore, the wavelength of the second harmonic is 4L/3. I simply rearrange this formula. And therefore, the frequency, which is equal to the velocity divided by the wavelength, is going to equal 3 times V/4L. So having looked at how that was calculated, we can put the numbers in. In my case, the length of the tube was 25 inches. And we want to put that value in meters. So to calculate that in meters, I'll multiply 25 by 0.0254 and 25 multiplied by 0.0254 is equal to 0.635 meters. The theoretical value for the first harmonic is going to equal 340 divided by 4 times this length. So if I calculate this, I get 134 Hertz. Let's look at the second harmonic. To calculate the second harmonic, that's going to be 3 times 340 divided by 4 times 0.635, which is basically just 3 times the value for the first harmonic. So I get 402 Hertz. In part 7, we compare our theoretical values obtained here with the actual experimental values. And I got quite close agreement although it wasn't easy to do, as it is quite difficult to sometimes hear those resonances. Okay, now let's look at the case where we have both ends of the tube open. In my experimental results, I obtained 246 Hertz for the first harmonic and 502 Hertz for the second harmonic. Let's have a look how to predict what the values for those harmonics should be. When we have the tube open at both ends, the waveform that will fit must have an antinode, a flow antinode, at the open ends. Here we see an example of the longest wavelength waveform that will fit, and you'll see hopefully that if I continue this line, we will see that the length of the tube now represents half a wavelength of the frequency at which the sound waves will resonate in this tube. So that's of course referring to the fundamental frequency at which they will resonate. So if we know that this length represents half the wavelength, therefore the wavelength is twice the length. Therefore the fundamental frequency is the velocity divided by 2L. The next waveform that also satisfies the conditions that there should be an antinode at both of the open ends is this one. And we can see here that actually, in this case, for the second harmonic, the length of the tube is actually equal to the wavelength, and hence the frequency of the second harmonic is equal to V divided by the length of the tube. So let's plug the numbers in. The tube was 25 inches as before, and we can use the result here for the length of the tube, which is 0.635. meters. The theoretical value for the first harmonic is going to equal 340 divided by twice the length. And that quantity is equal to, I'm just going to calculate it on my calculator, 340 So that's 340 divided by 1.27, which is 268 Hertz. And then the theoretical value for the second harmonic is going to equal 340 over the length, which is simply just double the value for the fundamental frequency, which gives me 535 Hertz for the theoretical values. And then once again I can compare the theoretical and the experimental values I obtained for the harmonic frequencies of the sound waves in the tube that was open at both ends. Finally, upload a picture of your mailing tube with the earbuds at one end to demonstrate that you actually performed the experiment. And that's it for the analysis.